Thank you for coming to my presentation. I'm Kohei Ito from Keio University. Today, I'd like to talk about implementing a multi-ejection switch and making the use of multiple lanes in a circuit switch multi-FPGA system. Recently, multi-access edge computing has gathered attention. The concept is computing at base stations. Timing critical jobs such as factory control and traffic control are processed. The power budget for MEC servers is restrictively limited compared with data center servers. Multi-FPGA systems are suitable for MEC. This is because FPGAs are more power efficient than CPUs or GPUs, and multi-FPGA systems can overcome the shortcoming of single FPGAs, which are limited by resource capacity. So we are developing flowing cloud system. It consists of multiple mid-range FPGAs, and they are connected by high-speed serial links. Currently, 28 FPGA boards are available in FIC. FIC's network is a circuit switch network with static time division multiplexing switches. Our goal is that the multiple FPGAs can be treated as a large FPGA virtually from application designers. This figure shows the diagram of a FIC board. We use Xilinx Kintex UltraScale FPGAs. Each FIC board has 32 high-speed serial lanes, and the bandwidth of each lane is 9.9 Gbps. STDM switch is a TDM switch whose configuration is set beforehand. In FIC, STDM switches are used as network switches. Its properties are small hardware and predictable communication latency. This figure is an operation example of a STDM switch in FIC. A packet of a certain slot can travel in the slot. For example, when slot ID of the switch is 1, a packet whose slot ID is 1 travels. So, minimizing the number of slots is important. It operates at 100 MHz and can transfer a 170-bit packet every 2 clocks. Furthermore, it supports multicast and broadcast, such as slot 1 in the figure. As mentioned earlier, our goal is that the multiple FPGAs can be treated as a large FPGA virtually from application designers. For the goal, high-speed communication between FPGAs is essential. However, FIC has 2 issues. The first is the effective use of multiple lanes. The second is a bottleneck in ejection ports. In FIC, Firefly cables with 4 bidirectional lanes are used as high-speed serial links. The picture on the left is a Firefly cable used in FIC. To maximize the bandwidth of Firefly cable, each FIC board has 4 STDM switches. In this slide, a bottleneck in ejection ports is illustrated. A STDM switch has only 1 port for injection or ejection. Multicast and broadcast can relax a bottleneck in injection ports. However, there is a bottleneck in ejection ports. We can't reduce the number of slots due to the shortage of ejection ports. Properties of multiple FPGA systems communication is different from those of NOX and HPC clusters. The interconnection network is directly connected to the user logic. FPGAs have many high-speed serial lanes such as GTHs and GTYs. So smooth data stream using the multiple cables large bandwidth is required. And multi-FPGA systems can face two issues we face. We have two proposals in this work. The first is a proposal of making the use of multiple lanes. The second is the implementation of a multi-ejection STDM switch. Here is some related work. Work 2 and 3 treated multiple lanes for circuit switched NOC. Work 4 proposed a non-contention ejection architecture for packet switched NOC. Work 5 proposed a packet switching router for FPGA clusters that support multiple injections and ejections. From here, I'd like to explain our proposal. The first is the proposal on making the use of multiple lanes. There are two methods to use multiple lanes: the link aggregation and the slot distribution. The link aggregation is a method that aggregates multiple lanes and regards as one lane. It increases the bandwidth. The slot distribution is a method that distributes time slots to each lane. It reduces the number of slots for a lane. Here is an example of a communication pattern with one lane. In slot 0, packets are transferred from node 5 to node 0. In slot 1, packets are transferred from node 5 to node 1. In slot 2, packets are transferred from node 5 to node 2. In slot 3, packets are transferred from node 5 to node 3. This is the case of applying the link aggregation with two lanes to the previous example. In slot 0, packets are transferred from node 5 to node 0 with both upper and lower lanes. The cases of slot 1, slot 2, slot 3 are the same as slot 0, and packets are transferred with both upper and lower lanes. In this example, the bandwidth is increased to 2 times by applying the link aggregation with 2 lanes. This is the case of applying the slot distribution with 2 lanes to the example of 1 lane. In slot 0, packets are transferred from node 5 to node 0 with the upper lane, and from node 5 to node 1 with the lower lane. In slot 1, packets are transferred from node 5 to node 2 with the upper lane, and from node 5 to node 3 with the lower lane. In this example, the number of slots can be reduced to half by applying the slot distribution with 2 lanes. The second proposal is the implementation of a multi-ejection STDM switch. As shown in this figure, a base STDM switch has only one port for ejection. So these two flows have to be assigned to different slots. Therefore, the number of slots is bound by the number of ejection ports. To relax the bottleneck, we provided dedicated ejection ports. The concept is the same as work 4, which is introduced as related work. For example, ejection port 0 ejects packets from input port 0. Now, I'd like to explain the evaluation. The evaluation environment and the topologies are as follows. Regarding the performance, we measured the computation time and the communication time. The computation time was obtained from the execution time of the calculation part of applications in HLS. The communication time was obtained by subtracting the computation time from the execution time of the entire application on the actual devices. We used some applications for the evaluation. The CG method is an algorithm that solves linear equations whose coefficients are positive definite symmetric matrix by an iterative method. It generates the same broadcast traffic at a fixed interval and is high computation ratio. We prepared different tool sizes. FFT is a high-speed algorithm to solve DFT. When the number of bots used is 2 to the power of n, it communicates with different n bots one at a time. It is high communication ratio. ReNet is a simple neural network that can recognize hard-written numbers from 0 to 9. It generates different traffic for each layer and is high computation ratio. At first, we are going to look at the performance of multiple lanes. This graph shows the execution time of the CG method. 2LA, 2LAX, 2SD, 4LA, and 4SD improved the communication performance. For example, by applying the link aggregation to the CG method on 4 boards, the communication performance improved to 1.65 times. However, 2SD could not improve the communication performance. Also, 2LAX 2SD could not improve as compared with 2LA. In this case, 4SD was better than 4LA on 8 and 24 boards. On the other hand, on 4 boards, the results were the opposite. This graph shows the execution time of the CG method whose matrix size is larger. In this case, 4LA was better than 4SD, which was different from the former results. This graph shows the execution time of the ReNet. Also in the ReNet, 4LA was better than 4SD. These results suggest that the link aggregation is superior for most cases. When the number of slots is large and the volume of traffic is small, the slot distribution is sometimes more effective. However, the link aggregation is superior for other most cases. Next, we are going to look at the performance of the multi-ejection switch. This table shows the number of slots which is required for applications. The multi-ejection switch can reduce the number of slots. For example, 8 boards CG method with base switches needs 8 slots. However, by using multi-ejection switches, we can reduce the number of slots to 3. The effect of the multi-ejection switch depends on the topologies. Regarding forward CG method with all-to-all communication, when the topology is a ring, the number of slots is 2. However, when the topology is fully connected, the number of slots is 1. This figure shows the execution time of CG method. The multi-ejection switch improved the communication performance. This figure shows the execution time of the FFT that applied the link aggregation and multi-ejection switches. It is possible to use multiple lanes and multi-ejection switches at the same time. By using the link aggregation and multi-ejection switches, we could improve the communication performance of the FFT up to 7.5 times. This table shows the resource utilization of the shell in XCKU 115. The resource utilization in applications such as VRAM, FF, and LUT is still small even with 4 switches, and enough resource was remained for application designers. This table shows the power consumption. The power of I/O, which mainly includes the power for transferring on Firefly, was increased by the number of lanes used. In conclusion, we proposed making the use of multiple lanes, the link aggregation, and the slot distribution. We could improve the communication performance by using multiple lanes. Moreover, we found that the link aggregation is better than the slot distribution in most cases. We also implemented a multi-ejection STDM switch, and it could reduce the bottleneck between a switch and the user logic. Furthermore, we tried to apply both the multiple lanes and the multi-ejection switches. As a result, we could improve the communication performance up to 7.5 times. I'd like to close our presentation. Thank you for listening.